Chapter 14, Oscillations. Oscillations cover simple harmonic motion, pendulums, damped simple harmonic motion, force oscillations, and resonance. You can find them in the timeline. Simple harmonic motion. We are surrounded by oscillations, motions that repeat themselves, such as guitar strings, drums, bells, diaphragms in telephones and speaker systems, and quartz crystals in wristwatches. Less evidence are the oscillations of the air molecules that transmit the sensation of sound, the oscillations of the atoms in a solid that convey the sensation of temperature, and the oscillations of the electrons in the antennas of radio and television transmitters. Oscillations are not confined to material objects, such as violin strings and electrodes. Light, radio waves, X-rays, and gamma rays are also oscillatory phenomena. You will study such oscillations in later chapters and will be helped greatly there by analogy with the mechanical oscillations that you are about to study here. Oscillations in the real world are usually damped. That is, the motion dies out gradually, transferring mechanics energy to thermal energy by the action of frictional forces. Although we cannot totally eliminate such loss of mechanical energy, we can replenish the energy from some sources to compensate for the mechanical energy loss to friction. Simple harmonic motion. Any motion that repeats himself at regular intervals is called periodical motion or harmonic motion. Simple harmonic motion, SHM, is a kind of periodical motion, which is a sinusoidal function of time. X at time t equals xm cosine omega t plus phi. This is a sinusoidal. Sine is okay too. If the particle vibrates back and forth, and this is a time, we extend it at a time, we find it like this one. And if we turn 90 degrees, we get this one. This is a time, this is this x, okay? In this case, the cosine is phi is 0. Why? Because at t equal to 0, this is 0, and x equal to xm. That means this is 0, okay?
Tuning forks create sound waves because of the side-to-side motion of their tines. But what is the exact form of that motion? We'll use this floppy version of a tuning fork with a light mounted on one of the tines to find out. When we set the fork vibrating and sweep it past the camera, the path of the light is a sine wave.
Simple harmonic motion. X at time t is xm cosine omega t plus phi. Well, this is called displacement at time t. This xm is the maximum displacement. You call it amplitude. This number is defined as a positive number, okay? And cosine changes between -1 and 1. This omega we call the angular frequency, and the total omega t for phi we call the phase. This is the angle, okay? This time t, this is called phase constant, or the initial phase, when t equal to 0, the initial phase. Frequency, or the numbers of oscillations that are completed each second. Okay? For example, called 10 hertz, that's 1 over a second. In 1 second, how many times? You have 10 oscillations. Okay. 1 hertz means 1 circular oscillation per second. period, the time for one complete oscillation. The period equal to 1 over f. For example, you have a frequency 10 hertz. That means that 1 second you complete 10 oscillations. For each oscillation, it takes time 1 over 10. So the relationship between period and frequency is reverse. Okay, t equals 1 over f, or f equal to 1 over t. So this is a simple harmonic motion. X at t equal to xm cosine omega t plus phi. Now we look at this two, the blue one and the red one. They xm are the same because the maximum displacement, this is x, are the same. But they repeat themselves, one circle, the time are different. The time different. This is the blue one is this t. The red one is this t prime. So the period are different. For these two lines, you see, their period are the same. Okay, maximum to maximum, maximum to maximum, minimum, minimum. Okay, but the amplitude are different. Okay, this is xm, xm prime are different. Look, these two, they have the same period, same magnitude, but it switched a little bit horizontally because of a phi. So the initial phase is different. The interpretation of an angular frequency omega. Well, the frequency is angular frequency. Well, the frequency is repeated. Okay, how many times you repeat in a second? The angular, so the angular frequency. We look at this one. Okay, we know the period are different, right? The amplitude are the same. T at time t, x at time t, you could xm cos omega t. What we call frequency, we see the displacement xt must return to its initial value after one period of time t. Let's see, after one period, this one, repeat this one. Or you get here, you repeat it here, okay? At any time, this is t must be any time. So we see, mathematically we see x with t equal to t plus period. This period. For the two period, the three period are the same. We with the shortest one period must equal to t. That's mathematics. The displacement is the same, x the same. And we put this one into this x, we get xm cosine omega t plus period t plus phi equal this t is this t, so xm cosine omega t plus m. This t could be any time or any t, not particular. And then we compare these two equations. Xm can cancel out, so the phase inside omega t plus capital T plus phi must equal to small omega t plus phi plus 2n pi, n 2 pi, or 2 pi n. We take n equal to 1 because it's the shortest, the latest, the shortest time. So in this case, we find we cancel out phi. We get a t equal to omega t equal to 2 pi. In other words, omega is 2 pi over t, or t is 1 over 5 frequency. So this is equal to 2 pi f. Okay? What do you call it? We call it angular frequency. This is frequency. We put an angle, 2 pi. So to get 2 pi, angular frequency. This is how I remember that one. Okay? So this is three. Angular frequency, period frequency, they connect with each other. Once we know one, we can find another two. The unit is called the radius per period, per second. Simple harmonic motion, SHM, has a property, its acceleration at time t equal to minus omega square x at time t. In other words, the acceleration is proportional to its displacement, with minus with constant. Now look at this one. This is a simple harmonic motion, sinusoidal displacement, okay? Sine or cosine. This is a curve. This is the cosine. This is x. This is a t. We find the v. What is the v? V is dx dt. And we do the derivative with the time t. Get cosine derivative with time t is minus sine plus omega. Okay, so get a minus omega xm sine omega t plus phi. Okay, or we can write it v equal to v maximum minus v maximum sines. We put this one, this is sine and minus. So this is sine with a minus. Of course, this is time t, this is a v. Okay, this is a v. Okay, okay. And we do the acceleration. A equal to dv dt. Okay. And we do this derivative with respect to time t again. Sine derivative sine is cosine and omega. So get the omega squared. So A equal to minus omega squared xm cosine omega t plus phi. And look at this xm cosine omega plus phi is exactly to x at time t. So we put this one here. It's minus omega squared t. Then you see we get the acceleration equal to minus omega squared t. Okay, this is a characteristic of simple harmonic motion. Okay, we plot this one. This is cosine 2. So like that, this one, and it's have a minus. So reverse. Of course, the vertical is different. This is acceleration. This is velocity. This is displacement. Okay. Now we find the maximum v. This one v omega x. The maximum a is omega squared xm. Okay, omega squared xm. And that v is between these plus or minus. A is between the plus minus. Okay, the conclusion. When x equal to 0, this is 0. A is 0. V is maximum. Okay, A is 0. When x is maximum, x maximum cosine is 1. So A is maximum. V is 0. Okay. This is a simple harmonic motion. They are sinusoidal function. And we have acceleration of simple harmonic motion equal to minus x plus x omega squared. So in simple harmonic motion, the acceleration is proportional to the displacement, but opposite indirect sign. And the two quantities are related by a square of the angular frequency. These you have to remember. The fourth law for simple harmonic motion. We look at this F equal to ma. When you do the simple harmonic motion, F must satisfy this one. And the A is the second derivative of its displacement with respect to time t. Okay, and we know this one. We put this equation, we get is equal to minus omega squared x. This is a caret. The black one is the characteristic of simple harmonic motion. Its acceleration is proportional its displacement with minus with omega squared. And we look at this f. This f is proportional to x. So that likes this likes a Hooke's law. Okay, Hooke's law is f equal to minus kx. So we compare these two. We find that k equal to m omega squared. Okay, and omega equal to k o m squared root. Okay. So we look at this one. This is this one. This block moves under the force of spring. The spring is satisfied this one. It must have simple harmonic motion. And the omega, the angular frequency equal to K over M. K is the spring constant of the spring, M is the mass of this one. Okay? And K is equal to M omega squared. This is the fourth law for simple harmonic motion. Simple harmonic motion must have a force which obeys the Hooke's law. The block spring system forms a linear simple harmonic oscillator at the oscillator, where linear indicate that F is proportional to X. So this is a linear function. And you plot it, it's a line, it's a linear, okay? Simple harmonic motion is the motion executed by a particle of mass m, subject to a force that is proportional to the displacement of the particle, but opposite in sign. Angular frequency, omega equal to K over M square root. When M is smaller, omega is larger. K is larger, omega is larger. Omega is larger, T is smaller, okay? So period T is 2 pi of C, 2 pi F omega of K, okay? This formula you have to remember. Every oscillating system, be it the linear oscillator of a diving burrow or violin string, has some proper elements of springiness and some elements of inertia or mass, and thus resembles a linear oscillator. In other words, linear oscillator has two elements. One is springiness and one is inertia or mass. Oscillator, these elements are located in separate parts of the system in some linear oscillator. The springiness being entirely in a spring, which we assume to be massless, and the inertia being entirely in the block, which we assume to be rigid. But, however, in violin spring, the two elements are both within the spring itself, as you will see in other clips. This is a Hooke from UK.
This heavy spring and this set of masses will be used to show simple harmonic motion. If we place 1 kilogram on the spring and set it in motion, the spring and weight oscillate with a regular period. What will happen to the period of oscillation if we increase the mass to 2 kilograms? The period increases. If we put an identical spring side by side with the first spring and repeat the demonstration, how will the period of oscillation change? The period decreases. We'll use this glider floating on a cushion of air and these springs to investigate simple harmonic motion. If a spring is attached to each end of a glider, the glider will oscillate back and forth on the track. What will happen to the period of oscillation if we double the mass of the glider?
The period double.
The top half of the screen shows the original arrangement, while the bottom half shows the glider with twice the mass. The period has increased. What will happen to the period if we add another spring to each end of the glider instead of more mass? The top half of the screen now shows the original setup, while the bottom half shows the glider with another set of springs attached. The period has now decreased. To show the form of this type of motion, We will mark one point on the glider and use it to draw a graph of position versus time.
Sample. A block whose mass m 680 grams is fastened to a spring whose spring constant K is 65 Newton per meter. The block is pulled a distance x 11 centimeter from its equilibrium position at x0 on a frictionless surface and released from rest at t equals 0. Question 8. What are the angular frequency, the frequency, and the period of the resulting oscillation? We said before, angular frequency, and the period, they are related with each other. So once we know one, we can find another two. Okay. By definition, omega equal to square root k of m. In this question, k is 65, m is 0.68. So remember, this one you have to use the standard unit called kilogram. Okay. So we get omega. Once we get omega, we get a t, get f. Okay. F equal to omega over 2 pi. Okay. And t equal to 1 of f, or 2 pi over t. T pi omega. We get this one. This is simple harmonic motion. What is the amplitude xm of the oscillation? Xm is 11. Okay? It's the maximum from energy conservation. What is the maximum speed Vn of the oscillation block, and where is the block when it occurs? Then we see the maximum velocity is omega xm. So we put number inside. When it happens, maximum is V is sine. When sine is maximum, cosine 0. So it happens when x at t equals 0. Anytime when x equals 0, you get a maximum V. What is the magnitude am of the maximum acceleration? Well, the acceleration is omega squared xm. You can find this one. Okay, where is it? X maximum, am is maximum. Okay. What is the phase constant phi for the motion? Then we know that when this is 11, this is 11, so this must be 1. Time equal to t, okay, and so the phi must be 0. Phi must be 0. Okay. What is the displacement function xt for the spring block system? Then we find everything, we put a number inside. Okay, so this is one formula. We put xm 0.11 with omega 9.8 phi 0. So we get xm concrete explanation is 0.11. This is unit meter. Cosine 9.8 t second. Sample. At t0, the displacement x0 of the block in a linear oscillator, like that of above equation, is minus 8.50 centimeter. When we do the calculation, we must use the unit meter, minus 0.0085 meter. This is what we read x0, we read as x at time z. The block's velocity v at time 0 is minus 0.920 meter per second, and its acceleration a at time 0 is positive 47 meter per second. Give you 3 initial conditions. Question A. What is the angular frequency omega of its system? Omega equal to square k over m. We don't have this information in this question. What we do, we have 3. Okay? We know x at time 0 is this. Y at time 0 is this. A at time 0 it is. We know this one. This number, no. And we want to find omega. We look at this one. This is no omega. You have omega. You have omega. And if it's xm cosine xm cosine. So we find out, we divided 0 minus divided x0, we can cancel out this one. We get omega squared. So you get this one. Then we get omega. Okay? Okay, once we get omega, see what else can do. Right? The angular frequency is frequency equal to angular frequency divided by angle, 2 pi. You get this one. Once we get f, the reverse is the time t. Okay? What is the phase constant phi at the amplitude xm? Now, we already omega. Okay? We want to find the phi and xm. We look at this v over this one. xm cancel out. We already have angular frequency omega. This is tangent theta. Okay? We get this one is tangent theta. So this number we know that. This one we know that. So can tangent phi. Tangent phi. Okay. Get this one and get a phi. This one you get a 2 angle. Either minus 25 or 150. Oh, this is you can go to 335 degree. Which one is right? Or both are right? Or both are wrong? And we see this one. We put this xm at time t. We put the phi 1. So xm, we know this one. Cosine with v, we get xm equal 9.4 centimeters. Then we check this one. We put the cosine minus 1, and then we put x0 and cosine minus, we get x this one. And we found this one is wrong. Why is wrong? Because our definition, the amplitude xn must be positive number, and there you get negative. So our answer is 150 degree. Energy in simple harmonic motion. We know x at t time t is xm cosine omega phi. And we know that when k equal to m omega squared. So let's see its potential energy. Potential energy a spring has equal to half k x squared. And we put x squared, we put this number. This is xm squared, cosine m squared, and put the k. And we know, and kinetic energy is half mv squared. V is derivative of x, we put it equal to minus omega xt, right? Yeah. So, okay, and then we see this m omega squared. M omega squared equal to k. So this one equal to rewrite half k xm squared. Potential energy, kinetic energy. We look at this one, the coefficient are the same. So we put them together, we get a mechanical energy. So the mechanical energy E equal to U plus K. We put them together, this is take this off, and cosine squared plus sine squared anyway is 1. So we get mechanical energy at any location x is equal to half k x squared. Now, this is a constant because this is the maximum constant. And also we look at the t. At any time t, they are the same. Okay, it's different. It's any location, any time. Well, actually, they can be the same, right? Yeah, that's constant. An oscillating system normally contains an element of springiness and an element of inertia. It uses the former to store its potential energy. This is a springiness. And the latter, called the inertia, store its kinetic energy. We look at this one. This is x is vibrate, okay? This is time, okay? And x equal to 0, the potential energy is like this one is 0. Okay. This is x equal to xm cosine omega t plus phi. And equal to kinetic energy equal to half mv squared. And when x equal to 0, v is maximum. See this one? V is maximum. Okay, we put a v. This one is half kxm. Why the half k? Because you do the derivative, you have omega. And you square k omega square equal k omega square m omega square equal to k. So we put this one. We see we put this kinetic energy and this potential always equal to this one. The total mechanical energy at any position is zero, is constant. Is constant. What is this? This is that when x is maximum, you don't have a speed. There's potential, total potential. And you look at this t. This is x t. A t goes by, it vibrates at any time. The total mechanical energy at any time is constant too, as we see before. Sample. What is the mechanical energy E of the linear oscillator of above sample? Above sample. Initially, the block's position is 11 centimeter, and the speed v0, and spring constant k is 55. Mechanical energy is very easy because you have a k, we have xm, so it was equal the maximum position energy. Okay, remember that one. This one you have to use the unit, standard unit, meter. So 11 centimeter is 0.11 meter. Part question B. What are the potential energy U and the kinetic K of the oscillator when the block is at half? What are they when the block is at minus half? That's very easy. Very easy. The U equal to half mk. When the kx equal to half core, this is energy. And this energy turned out the 1/4 total energy. And the leftover is the kinetic energy at this time. Okay? So it's about 3/4 E. This kinetic energy. Now, what is the kinetic energy and the potential energy at x equal to minus? Same thing.
Here is a device called a torsion pendulum. It consists of a flexible brass rod which is held tightly in an upper support and which has a heavy disc attached to its bottom end. If we twist the rod by rotating the disc and then release it, the pendulum oscillates. If we double the mass of the pendulum by adding this ring to the disc, how will the period of oscillation change? The period increases.
Pendulums. Torsion pendulum. If we rotate the disc from its rest position, this is rest to indicate by a reference line marked 0, and release it, it will oscillate about that position in angular simple harmonic motion. The twist in the suspension wire store the potential energy and provide restoring torque. Torque equals minus kappa theta. Here kappa is a constant called the torsion constant that depends on the length, diameter, and material of the suspension wire. So we know that the torque around this one for the disc, okay, the torque is I alpha. The alpha is the second derivative of theta respect to time t. And in this case, is equal to minus kappa theta. So we get again differential equation. Okay, this equation looks familiar. Okay, We remember that Hooke's law, F equal to minus kx. We get if a system vibrate under the Hooke's force, it is a simple harmonic motion. Okay, and we have this one, acceleration, okay, equal to derivative, second derivative of its position x with respect to time t. Will have some property? Yes, it has. It is proportional to displacement xt with minus and with a constant. This constant we call omega squared, right? Yeah. And we multiply by m on this equation. Okay, this is f, okay? This is f. F equal to minus kx. F minus. And here with a k equal to m omega squared, okay? So the omega equal to k over m squared. Once we know the omega, we can know the period t equal to 2 pi over omega, right? Yeah. And then you look at this equation, okay, this equation, all right? Kappa over I theta that equal to minus omega squared t. So we see the omega squared equal to kappa over I. So t is 2 pi omega, 2 pi I over kappa square root. This is a formula for period of this pendulum. Sample. As fig A shows a thin rod whose length is 12.4 centimeter and whose mass is 135 grams, suspended at its midpoint from a long wire. Its period TA of angular simple harmonic motion is measured to be 2.53 seconds. An irregularly shaped object, which we call object X, it then hung from the same wire, same kappa, okay? And its period T measured is TB, 4.76 seconds. What is the rotational inertia of object X about its suspension axis? Now, this is we know that one. The I. This I is around the center of mass, so equal to m L squared over 12. Okay, here m is 135 grams. We have to convert it to kilogram, 0.135 kilogram. And L is 12.4 centimeter. We have to convert it to meter, 0.124 meter. So this is I know this one. And I know the T, okay? T equal to 2 pi over IA over kappa. Kappa, I don't know. But I know A, I notice I can find the kappa. I put the kappa inside, okay? I know this one, I can calculate Ix. This is what we want to find. And we do it in different way. We square on both equations, on both sides, and we cancel, divide it. And finally we find that Ix equal to IA times Tx squared over Ta squared. And we put everything in. We get rotation inertia Ix, this one around this axis. Okay. Pendulus. A simple pendulus consists of a particle mass m, called the bob of the pendulum, suspended from an unstretched massless string of length L at this point. The bob is free to swing back and forth in the plane of the page, to the left and to the right of a vertical line, so the point at which the upper end of the string is fixed. The element of inertia in this pendulum is the mass of the particle, okay? And the element of the springiness is in the gravitational attraction between the particle and the earth. So it can vibrate, You have two elements. We look at the free body diagram. This is the mass, okay? This air, M. It's vibrates back and forth. How many forces acting on it? Two. One is tension, one is gravitational force. What's the move? It's vibrate around this point, okay? So what we have is, you see, this kind of is called a simple pendulum. What do you see? The top around this one. We have this T does not have top around this one because you don't have R. Only gravitational force. What is this? We call it air F perpendicular. Remember that? What is perpendicular? Perpendicular to the air. This is one. So this one is mg sine theta. This is the air F perpendicular. Okay? And since it's very small, so we call this phi f mg theta. And for this rotation, we know tau equal to I alpha. Okay? This is second derivative of theta respect to time t. Okay? And we know tau equal to this one. All right? Now we from this equation, we find this one alpha equal to this one equal to this over I minus mi. Now, we see the acceleration is perpendicular to the displacement. Minus and constant. This constant is omega squared. So omega squared equal to mgl over I. Okay. Here, the I is ml squared. We put this one fine, we find that period. So put ml squared, ml, the g over l. So omega equal to g over l square root. And the period is 2 pi over omega, we get 2 pi l over g. This is a period for simple pendulum. The physical pendulum. Most pendulums in the real world are not even approximately simple. This figure shows a generalized physical pendulum, as we usually call realistic pendulum. It's not thin, okay? Its weight is mg, and its hand at the center, O, and its center mass, C, okay? O is supporting point, C is the center mass, and the OC called H, okay? I is the rotational inertia of the pendulum about this axis, so this point supporting perpendicular to the plane, the swing. And we see the period of this physical pendulum, the 2 pi square root I O mgh. I'm going to prove it for you. Well, look, this one is a rotator on this one. So we have a tau. What is tau? Tau is equal to I alpha, based on the Newton's second law. Okay, and this tau, from here, only one forces, two forces, mg. Okay, r cross f. This is only f. This r cross f. Okay, then equal to r f perpendicular. This r is h. Perpendicular is this one. Perpendicular this r. So this one is f mg sine theta. When theta is small, sine theta approximates to theta. Okay, so this tau equal to minus h mg. Why is minus? Because theta is go this direction, is positive, and the torque is go this direction. So if theta is go this direction, the torque is go this direction. So always again the positive theta. So you have a minus. Okay. Well, this one we see alpha equal to tau over I. This is a tau. So we see the alpha is proportional to theta. have a minus, this constant is equal to omega squared. Okay, this is omega squared. So get omega squared equal to mgh over I. This I we have to measure, okay? And then the period is 2 pi over omega. We get 2 pi I over mgh.
This aluminum bar hangs from a bearing support so that it swings like a pendulum. If we compare the period of this physical pendulum with that of a conventional pendulum made of a string and mass, we see that the physical pendulum has a shorter period. To match the period of the physical pendulum, we need a string pendulum that is 2/3 the length of the physical pendulum.
Simple pendulum is a special case of the physical pendulum. This is a simple pendulum. This is I equal to ml squared. And H equal to L. This is center mass to this one is L. So we put the formula for the physical pendulum, I equal to ml squared, okay, H equal to L, and we get ml squared, HL, cancel M, L, we get LC. This is a period of a simple pendulum.
These two pendula have the same length but different mass. How will their periods of oscillation compare? Their periods are equal. Mass has no effect on the period of a pendulum.
Measuring G. We can use a physical pendulum to measure the free fall acceleration G. Countless thousands of such measurements has been made during geophysical prospecting. This is a profession which is looking for a gold mine, something, petrol, and so on. Now, we know the period for a physical pendulum is 2 pi square root I mgh. Okay, this we can measure. Okay, we can measure very accurately. Okay, and this we can calculate or measure. So we know H, we can find the G. For in this one, this I is 1/3 ml squared. This is a rho for one end, so 1/3 3. And this H here is H is half L. Okay, we put one inside, we get a G. Okay, and we measure T, we measure L, we can find the G. Okay, by measuring L and the period of T, we can find the value of G. If precise measurements are to be made, a number of refinements are needed, such as swimming and the pendulum in an evacuated chamber and so on. Sample. In figure 8, a meter stick about a pilot point at one end, at a distance h from the center of mass. What is the period of oscillation T? Now we can do this one. This I is 1/3 ml squared. H equal to half L, right? Yeah. And we put this Y, we get a T. Okay, we cancel the ml, so we get T equal to 2 pi 2L over 3G. All right, what does this mean? This means 2L over 3 sending another length. This is 2/3 of G. This is another simple harmonic period. Okay, so we can find this one period. We have seen in demonstration 2/3 of the length, they have the same period. To every point of suspension O of a physical pendulum, there corresponds a center of oscillation P. Distance from O by the length of the equivalent simple pendulum. This is 2/3. Okay. The physical pendulum had the same period while it is suspended from O or from P. You suspend here, you suspend here. The oscillation period will be the same.喂，喂，奶奶，侬講啥個？唔知你有嘅呀？就到了那個石庫的隔壁。哎，對個，37，不要客氣。哦 ，OK， 好。奶奶，喂。To every point of suspension O of a physical pendulum, there corresponds a center of oscillation P. Distance from O by length of an equivalent simple pendulum. The physical pendulum has the same period whether it is suspended from O or from P. We have seen now on the clip. For this case, is 2/3 of length. Okay. 2/3 of length. So the equivalent length is 2/3 of this. Question B. What is the distance LO between the pivot point O of the stick and the center of the oscillation of the stick? Okay, we look at this one. We have to show this one. This is 2/3. Okay. Now we put the number inside. Okay. So we'll get about, in our case, about 66.7 centimeter.
Here are 4 metal arcs, each of which is an increasingly large portion of identical circles. Each arc has a hole at the top for a pin support on which it can swing like a pendulum. Which arc will have the longest period of oscillation? All 4 arcs have equal periods.
Example. In the figure, a penguin, obviously skilled in aquatic sports, dives from a uniform ball that is hinged at the left end and attached to a spring at the right. The ball has length L 2.0 meter and mass 12 kilogram. The spring constant K is 1,300 Newton per meter. When the penguin dives, it leaves the board and the spring oscillating with a small amplitude. Okay. Assume that the board is stiff enough not to bend, and find the period T of the oscillation of the board. We look at this one. Okay. The torque equal to L F. Okay, F L. Okay, F is going down, and this one shows 90 degree. Cosine 90 degrees is 1. Okay, okay. What is F? F is minus K. This is X minus K down. this is x minus up, okay? The torque is this one, okay? And this is always this, the torque equal to I alpha, we'll put equal to L minus K. This I is around this one, so it's mL squared over 3. You can check the table, okay? The alpha is equal to this A over L, okay? And then we see this one, torque, okay, equal to this. This two are the same thing. And we cancel the one L, okay? We found that this is equal to MC, this is L, okay? And this L cancel out. And finally, we found A equal to 3K KO over M times X. Now, this is acceleration, this point, linear acceleration. This is X, is this length, okay? This A is derivative of 2. So in this equation, we find A is proportional to X. You have a minus, so this coefficient is omega squared. Omega squared. So we got a omega, we got a T. We got a T. Okay? We put in the main side, okay, we get 0.35 second. This one is nothing to do with M, with the length. The length nothing to do. Shorter, longer, okay? Simple harmonic motion and uniform circular motion. We see this is the Jupiter and its moon, the callisto. We look at this one, we know this its moon is move around it, but when we watch it, it looks like simple harmonic motion. So we find we can relate it, the simple harmonic motion, with uniform circular motion. Simple harmonic motion is the projection of uniform circular motion on the diameter of a circle in which the latter motion occurs. You look this one. This is the P. It goes circular, uniform motion. And the project, this P by P, is along this one cycle, it moves this one, okay? And we see this M prime moves in uniform circle, and the P is moved in simple harmonic motion. How I see this one? You see this X. The X equals R cosine XT equal to, in this one, equal to R cosine omega t plus T, okay? What is R called XM, okay? XM, all right. And we see this is velocity, okay? This velocity equal to minus x to c. And this is acceleration. We have proved it before, okay? Yeah. Proved it before. So we find out the simple harmonic motion, this one, is the project of uniform circular motion on a diameter of the circle, okay?
This rotating disc and a weight on a spring will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed of the disc. If we set the weight oscillating in time with the spot on the disc, the weight is always at the same horizontal level as the spot.
This rotating disc and this pendulum will be used to show the similarity between uniform circular motion and simple harmonic motion. A spot on the edge of the disc allows us to see the constant rotational speed. If we start the pendulum swinging just as the spot passes the pendulum stays in a vertical line with the spot.
Most methods of determining an object's mass actually measure its weight, the gravitational force the Earth exerts on the mass. Is there any way to determine the mass of an object in a weightless environment like outer space? This inertia balance is one way. These two flexible metal arms support a small platform which can hold various masses. If we put this mass on the platform and give it a push, the platform oscillates at a regular frequency. What will happen to the frequency of oscillation if we add more mass to the platform? The frequency decreases. This technique is used by NASA scientists to determine the mass of astronauts while they are in orbit around the Earth.
We'll use two audio oscillators of adjustable frequency to produce Leger figures on this oscilloscope screen. This oscillator drives the vertical motion of the oscilloscope spot. This oscillator drives the horizontal motion of the spot. When the two motions are combined, the pattern is chaotic until the frequencies of the oscillators are equal or are integer multiples of one another.
Two, one. Three, one. Okay. Damped simple harmonic motion. Damped simple harmonic motion. When the motion of an oscillation is reduced by an external force, the oscillator and its motion are said to be damped. In this case, without the bottom part, this is called simple harmonic motion. But we connect this map with an organism put in the water, so it will have a resistance proportional to the velocity, the FV called minus BV. In this case, we put in sign. So sigma F equal to Hooke's law and resistance velocity. What is this one? This is equal to dV dt. This one, sigma F equal to MA. Right? Yeah. This is equal to MA. This is equal to minus K. V is dx dtB. Okay. This equation, we rewrite it. Okay. M dx dt, move this here. B dx dt plus x dp. This is a second order differential equation. Okay. Linear, because it's all linear. And we want to find the answer of this one. We know that one, once you have this term, IBT, the vibration amplitude gets smaller and smaller. So we assume beside the xm cosine t, you have another term, E minus AT. As time goes up, this one goes down. So it gets smaller and smaller, okay, reduced, okay. So we assume the answer is this one, and we put this one here. We can do the derivative, okay. So you have two terms. The first term is minus A plus E cosine, okay. And second term is cosine is minus sine, and had omega, okay. So we had a blue one, 1, 2, 3. First one is the red one. So we have two terms. What is this one? And we see the second derivative. So we do this and do this. Do this, is minus A again. Minus be the xma squared. Okay. And the second is you cosine. Cosine is minus sine. Minus positive. With xm a minus c is omega. It takes the omega sine. And this one you have minus a minus. You get a positive xm a omega. Okay. And got a second you have cosine. It's minus cosine omega. This is omega squared. Omega. So we get this too. Now, let's multiply k on the side because you have kx. And then we multiply b on this side. You have b multiplied on this one. And second derivative, you have m. You get an m. And then we put them together. Now, here you get an mx second derivative plus b dx. This is equal to 0. And here we see a lot of sine and cosine. And we combine all the cosine term and all the sine term. We see the cosine term. This one, you had a kxm. This one is minus bxma. Okay. This one, you have positive mxma squared. And this term, minus x omega squared mx squared. This one. Sine. This is sine. You have b minus b xm omega. Minus b xm omega is a sine. Another sine is, let's see, m xm a omega. M xm a omega is 2 max omega. So this one. Now look at this equation. This equation should be equal at any time. What the result? The result is only possible is the coefficient equal to 0. Okay? All that we make this equal to 0. Okay? You cancel the omega xm, so you get the a equal to get a b equal to minus b a equal to b over 2m. Now we get this one. Relative b and m. You put a and inside, we get omega. Omega equal to k of m, b of m squared. And k over b is omega 0 squared. So originally, usually this term is much smaller than this term. We drop it. Get the frequency. It does not change too much. Okay. All right. We have a, then we get answer. We get omega. So x equal to xm e to the minus b over 2m. Okay. Cosine omega. This omega is this omega plus 5. Okay. Then the oscillation. This is the one. Beside the vibration cosine, we have external potential okay, term is minus. So as time increases to 0, this term decreases to 0. Okay, go to 0. All right, and then we have omega equal to this one. Okay, now we look at when the vibration, this one we call terms amplitude. Amplitude gets smaller and smaller, smaller and smaller as time goes by. Okay. Now we see the energy. The energy could have mxm squared, and at time t, because this term changes, so this becomes xm plus this is square to e minus bt over m. So the energy get less and less where it is consumed by friction. Okay. The mechanical energy decreases exponentially with time. Sample. For the damped oscillator of the figure, M 250 gram, K 85 Newton per second, and B is 70 grams per second. What is the period of the motion? We just put in the formula. Okay. Km is 0.25 kilogram. B is 70, okay? This is, we should use the kilogram. So it's a 0.07 square, okay? Yeah. And this one, we find out B is much, much smaller than KB. So this term can be dropped. We get this one, okay? So omega equal to omega 0. Okay? And the T is the same thing. Very easy to find out, okay? How long does it take for the amplitude of the damped oscillator to drop to half its initial value? Initial value is this one. Now we got half. What is half? Half this one, okay? Now, this half this one. Now, when t equal to 0 is xm. How long it got half? And we did so. We cancel the xm, we do the log. So, okay, this is equal to log this equal to log half. Okay, log 2 half. This side we get minus bt over m. Okay, and this side we get minus log 2. They are equal. Okay, then you find this one. The t, okay, is log 2, 2m log 2 over b. We find the answer. Question C. How long does it take for the mechanical energy to drop to 1/2 its initial value? This is amplitude drop to half. This is energy drop to half. Then we see what the energy? Energy equal to half m xm squared times t. And you have this t. Okay. This is equal to half 0. E0. E0, this is equal to 1. So equal to half E0, half fmkxm. Then we see cancel the half k, cancel xm, we do the log, we can find the t. Okay, similar to this one. That's it. That's it, only 2.5 seconds faster than the amplitude deteriorate. Forced oscillations and the resonance. Forced oscillations and resonance. A person swings passively in a swing is an example of a free oscillation. If a kind friend pulls and pushes the swing periodically, we have forced or driven oscillations. There are two angular frequencies. One, the natural angular frequencies omega of the system, if the system oscillates freely. 2. The angular frequency omega d of the external driving force. A forced oscillator oscillates at the angular frequency omega d of the driving force, and its displacement x at time t is given by x at time t equals xm cosine omega dt plus phi. So this is called the driving frequency, where xm is the amplitude of the oscillations. When omega d, the driving frequency, equal to natural frequency omega, then the resonance happens. A condition called resonance, at which the displacement amplitude xm of the oscillations is greatest. All mechanical structure have one or more natural frequencies, and if a structure is subjected to a strong external driving force that matches one of these frequencies, the resultant oscillation of the structure may rupture it. Look at this one. This is the amplitude, okay, of the swing. This is the ratio of the driving force frequency and natural frequency. If they equal to 1, then you have a resonance. The amplitude is the maximum. These three layers is because of the resistance of external force be different. Okay?
This bowling ball pendulum will be used to demonstrate resonance.
The pendulum swings with a natural frequency of about 1 swing every 2 seconds. We'll drive it by striking it with a rubber mallet. First, we'll drive the pendulum by striking it repeatedly at short intervals. Even after many blows, the pendulum isn't moving very far. But if we change the striking frequency to the natural frequency of the pendulum, the amplitude increases with each blow of the mallet.
This physical pendulum drives a rocker bar, which in turn drives 3 simple pendula hanging from the bar. The driving frequency can be changed by moving a weight on the physical pendulum. The weight is first adjusted so that the driving frequency is equal to the natural frequency of the longest pendulum. If the 3 pendula are initially stationary, only the longest pendulum responds strongly. The weight is now adjusted so that the driving frequency matches the frequency of the middle pendulum. Notice the strong response of the middle pendulum and the different phase lags between the driver pendulum and each of the 3 simple pendula.
This spring and weight hang from a driver whose frequency can be adjusted with this control. We'll increase the driving frequency slowly and watch the effect on the motion of the weight. At low frequencies, the mass moves very little. As the frequency increases, the amplitude of oscillation increases until the mass strikes the table. The weight is now lagging behind the driver, which is moving at the resonant frequency of the spring and weight. When the frequency is increased further, the amplitude of oscillation decreases.
We will demonstrate resonance by breaking a glass beaker with a sound wave. This beaker has a natural oscillation which can be produced by gently tapping its brim. We create a resonance by exposing the beaker to a sound wave of the same frequency. For this demonstration, we use a stable oscillator, a power amplifier, and a horn driver which can handle a large amount of power. The beaker is positioned on a foam rubber pedestal in front of the hole from which the sound emerges. The sound wave emitted by the vibrating beaker is picked up by the microphone to the left of the beaker and displayed on the oscilloscope. The oscilloscope is triggered by the signal from the oscillator, but displays the signal emitted by the beaker, so that both the amplitude increase and the phase shift can be observed as the frequency is tuned through resonance. The frequency of the oscillator has now been set to the natural frequency of the beaker. Using a stroboscope, the oscillations of the brim of the beaker can be viewed from above. Returning to a front view of the beaker, we now increase the amplitude of the sound wave until the oscillation of the beaker exceeds its elastic limit.
This pair of physical pendula have the same period. If we connect the pendula together with the light spring and set one in motion, the second pendulum also begins to move. Soon both pendula have nearly equal motions. Now the second pendulum has all the energy and the first pendulum has nearly stopped. The energy has now gone full cycle, with the first pendulum in full motion and the second at rest. If we connect the two pendula with the stiffer spring, the energy is exchanged much more quickly. If we change the period of one of the pendula by moving a weight, the energy no longer passes completely from one pendulum to the other.
Here is a device called a Wilberforce pendulum. It can oscillate in two ways: vertically and back and forth in torsional oscillation. After the pendulum is made to oscillate vertically, energy begins to transfer into torsional oscillation and the pendulum begins to twist. After a while, most of the energy of the pendulum is in torsional oscillations. The pendulum is barely moving in the vertical direction. Then energy begins to transfer back into vertical oscillations. Eventually, nearly all the energy is in the vertical oscillations, and the cycle begins again.
By the mid-20th century, the suspension bridge had come into its own. But in November 1940, something happened that would change these bridges forever. The Tacoma Narrows Bridge in Washington State opened in July 1940 and hit instant fame. Christened Galloping Gertie, this newly opened bridge began to oscillate uncontrollably.
It's making the hairs on the back of my neck stand up as I think about it, because you just don't want to go there. You know, it's a horrible, horrible thing.
On the 7th of November 1940, Galloping Gertie collapsed. For designers, nothing would ever be the same again. The collapse of the Tacoma Narrows was a wake-up call for suspension bridge designers. In pursuit of slenderness, they'd underestimated the power of wind. The mystery lay in the fact that Tacoma was designed to withstand 120-mile-an-hour winds. Yet the wind speed on the 7th of November 1940 was only 40 miles per hour. The key to unlock this mystery would be found in a phenomenon called natural frequency.
Natural frequency it would be something that's very familiar to anybody who likes music. It's the note that something makes. And if you pluck a guitar string or a violin string, you hear a note which has a particular frequency. And bridges are no different.
We've got three structures here. They've each got a different natural frequency. The natural frequency is the frequency it wants to vibrate at if you just give it a twang. And so we've got a really slow natural frequency here, got a really fast one, and we've got one in the middle.
In this test, the Tacoma Narrows natural frequency is most similar to the slow one. When winds hit a bridge, they create mini whirlwinds, called vortices. The problems start when these vortices have the same natural frequency as the bridge. This is called resonance.
If I now start to shape this support for these three bridges, if I do it really slowly, just give it a little motion, at the natural frequency of my big slow one, you can see that the big slow one really starts to respond, and we get massive amplification, and the other two are hardly doing anything. If I do it at intermediate sort of speed, the middle one goes wild and the other two stop. And if I go really fast, just a little one goes wild and the other two stop.
On that morning, with vortices created at the natural frequency of galloping Gertie, it was only a matter of time before resonance caused the bridge's collapse. Tacoma terrified bridge engineers. Suddenly, wind was the enemy. They went back to the drawing board and discovered that the way to combat resonance was to bolt extra beams underneath the deck, called a stiffening truss. At vast expense, bridges around the world, including the Golden Gate, were retrofitted. It seemed the stiffening truss was the only way forward. That was until the late 1950s, when a young British designer came up with a new idea. And after countless awards, more than 40 years later, Bill Brown still plays down his role.
I think I was probably at the right place at the right time, in fact.
The magic of Bill's idea was to work with the wind rather than against it.
I didn't know that it would work aerodynamically. I knew it would work structurally, but not whether the aerodynamics would work.
Bill came up with the idea of reshaping the deck of the suspension bridge to make it aerodynamic. The wind is deflected around it, and the deck flies in the wind. Bill had just finished the 4th road bridge and had won the commission to build a crossing over the River Severn. This would be the first bridge in the world to have this new deck. But first, he had to test it. 40 years later, Bill demonstrates what his wind tunnel tests showed. First up, he tests the Tacoma deck.
You can see the Tacoma narrows section is twisting quite violently.
At just 40 miles per hour, the Tacoma deck cannot withstand the wind.
We now have mounted the 7 cross-section, and we're running this now at 150 miles an hour. As you can see, it is absolutely stable. This is because we have an aerodynamic section, the wind is flowing above and below it, streamlined, and the forces are low.
The Severn Suspension Bridge was opened in 1966 and would lead the way in modern bridges.
The magic is that it is streamlined and therefore the wind forces are low and there are very few vortices. So generally speaking, we don't need to add structural resistance to overcome the wind forces.
After the success of the Severn, bridges around the world were built with aerodynamic decks, starting with the Humber. Resisting wind and earthquakes is a challenge, but there are other forces of nature out to get the suspension bridge. Over the years, engineers thought they understood the effect of people walking on a bridge, but they didn't.
Down you two! Break step!
Everybody knows about the Roman army having to break step when they go across bridges, and the reason for that is because they march very regularly. You have lots of people all putting their feet down at the same time, and if you get a bridge which happens to have a frequency which is close to that, the Romans must have found out 2,000 years ago that if they didn't break step, they would actually knock the bridges down.
Next chapter. Chapter 15, Waves. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They help a lot. I'm sorry for not remembering its name to show my appreciation. It seems that They came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.